Hi, let's talk about how you could improve your mathematical insight, which is maybe one of the hardest things that you could be trying to do in mathematics, but also hopefully one of the most beneficial. So you really want to focus on what are you trying to get better at, because this is really different than learning a new math technique or learning a specific mathematical concept. For those ones, typically you see example problems, you try and focus on what's important in those example problems and make sure that you can reproduce it. But the whole idea of mathematical insight is it's useful for problems where you don't know what to do, where you've never seen the problem before. So you need to study for them in a different way. So what are you really trying to improve? It's two things. It's noticing things about the problem, and then connecting those aspects of the problem to math you already know. So practicing noticing and connecting is what we're going to be talking about for the rest of the video. So the other half of this is a lot of students say, how do I practice? But I want to emphasize, when do you practice this? It's too late to practice mathematical insight the day before the test, or even 3 days before the test, or even a week before the test. You only get better at mathematical insight kind of slowly over time. So you want to be practicing it a little bit every day. And that's why every single problem set has a learning problem at the back. That's one of the key ways you can practice. A lot of the stuff we do in class is also an opportunity to practice, but only if you realize that's what you should be doing and you focus on the things you need to focus on to improve mathematical insight when you're working on those problems. So I'll have some tips right now for what can you focus on before you try the problem, while you are trying the problem, and after you see a solution. Because after you see the solution, that's one of the key places where I think that you can grow in this area. All right, so before you start the problem, it's really hard to connect to math you know if you don't have like an immediate sense of what are all of the basic things that I know from this unit. So if I asked you to list what are all the basic things you know in the unit, could you just rattle off a whole list of things? A lot of students who struggle in this area, the answer is no. They have to sit there and kind of puzzle over it. They're like, well, what have we done? We've done like moving stuff, vectors, but like see how those are kind of vague? It's better if you can have a list like, we know how to find the length of a vector. We know how to construct a vector pointing in a particular direction. We understand how you can scale a vector with time to make it longer or shorter so that it has a desired length. So each of these are very specific techniques. So that's the first thing, is try and make sure that you understand what specific techniques you already know. And it doesn't have to all be in your head. You can definitely like brainstorm a list on a piece of paper. But if you have a whole bunch of things sitting on a piece of paper in front of you, you're more likely to say, oh, wait a minute, I bet the thing in this problem connects to that one of them, and be able to point at one in particular. So then the other thing that you should have kind of preloaded before you start the problem is a list of the problem-solving strategies. Excuse me. As you remember from class, when we've done this, often a lot of these problem-solving approaches overlap with each other. But this is kind of the list that we've had in class so far. You can explore small examples with specific numbers if it's a general problem with variables. You can visualize the problem to help yourself really get an intuitive feel for what's happening. A great thing to do is to write all the things you know, and then to write what you want to know. But the key is to use mathematical notation. So if you want a linear path, it's helpful to actually write what a linear equation looks like, because that can focus you on specific things you want, like, oh, I want a slope and a y-intercept. And then you can start thinking about what connects the things you know to the things you want to know. Sometimes it's not obvious, and so you can also ask, what else could you figure out about the problem? Like, what other facts could you know, even if they don't seem like they're related to the solution you're looking for? Because you could still maybe use them to make further progress. Almost all of my problems are variations on problems that you've seen at some point in the past. So it's really helpful to think, where have I seen this problem before? And what's making this one different? And then you can focus in just on the difference. Solving a simpler version of the problem first, and then using that to leverage into the more difficult version of the problem. breaking the problem into pieces, particularly problems that have like a lot of different constraints or a lot of different requirements. Choose to ignore some of them and say, well, what if I just look at the speed first? How would I think about that? Or what if I just look at the y-intercept first? How would I think about that? And solve the problem one piece at a time. A great strategy when comparing to other problems is asking what specific part of this problem is making it difficult to solve, and how could you start addressing that? And a really useful one in all circumstances is changing up the representation you're using. If you're trying to come up with an equation, usually it's too hard to come up with an equation directly. You need to use some other thing to show you the pattern that the algebra is supposed to represent. So you could write down what you want in a table or a graph, and then think, all right, what equation would describe what I'm seeing on my table and graph? Not just those representations, but different algebraic forms. So we've said parametric equations are really just a notational difference from vector notations. Vector equations. It is two different ways of thinking about them, but you can kind of intertranslate between them. We've talked about how you can go back and forth between polar ways of thinking and rectangular ways of thinking. And so if you're working in a rectangular setting, but you notice that there's a lot of things about turning and rotation, it might help to rewrite your problem all using polar notation instead. So those are some examples, but it would probably be more helpful to actually look at some illustrations of this, so let's do that. Oh, sorry, let's not do that yet. So that was before the problem. So before you tackle the problem, what are the basic skills? What are my problem-solving strategies? Have those lists sitting in front of you. Then while you're trying to solve the problem, expect that problems like this, you don't just sit down and solve. You might need to spend 10 to 30 minutes a couple of times separated in time. Because the whole trick is you need to be able to see the problem from different perspectives, or you need to have a good idea that will let you connect math you know. And you can't expect that to happen in one sitting necessarily. So you need to plan out ahead of time to give yourself enough opportunity that you can get lucky in the right way. A lot of students that I see are very focused on the question, how can I solve this? Which might seem like, of course, that's what you're focused on. But questions that you've never seen before, very often you have to take a roundabout route to solving them. If you're so narrowly focused on how can I get to the solution, you're not going to see the stepping stones you need to use to actually get there. So rather than being so driven by how can I solve this, you want to ask, how can I learn more about the problem? How can I take a new perspective? What stepping stones can I use that will take me in the direction of understanding more? And if you go in the direction of understanding more, hopefully eventually you get to a solution. But there is no shortcut for this kind of problem. Like, that's the only way. And the most important piece of advice, we practice these skills a lot, but a practice only makes perfect if you know what to focus on and you're taking away the right things. So every time we do one of these problems, you're never going to see that problem again. So you don't want to try and memorize what were the steps to the solution here. Instead, you want to go back and put yourself in the mindset where you were originally looking at the problem and think, all right, so what was lying under the surface of this problem that I could have noticed that was important, but didn't originally pop out at me as being important? You could think, what stepping stones could I have taken initially to make progress? What were the clues that a certain idea was the right idea to connect? Because it's those associations that you're going to reuse, not the exact steps for this exact problem. So again, it's a switch in focus. You want to focus on seeing the problem differently, on being able to recognize the difference between the surface appearance of the problem and what are the underlying mathematical structure that the problem really has. All right, so come back in the next video and we'll do some examples. So one example from class was understanding why polar graphs look the way that they look. So we plotted this polar graph of sine 2 theta, and we said, oh, 2 theta has 4 petals. I wonder why that is, and I wonder why they happen where they do, and why they have the shape that they do. And then we noticed that with 4 theta, we have 8 petals. So 2 theta gives you 4 petals, 4 theta gives you 8 petals. Why is that pattern happening? And then 3 theta gives you 3 petals, not 6. So why is that pattern happening? All right, well, how can you use what I just described to answer this kind of question? 2 really great problem-solving strategies you can use are connecting to another representation. So if you just stare at this equation and kind of hope that an idea is going to come to you, that's not really how problem-solving works. You don't solve problems by staring and hoping an idea comes into your head. You got to try things. You got to get things on the paper in front of you before you can start noticing what connects to what. So let's compare this polar version to the rectangular version, and let's kind of interpret corresponding parts of the equation in the same way. So here we can interpret x as being the angle and y as being distance from the origin, which is what they mean over here in the polar version. And now you can start noticing some similarities. Over here, it's familiar that the range of sine goes from -1 to 1, and here you're noticing, aha, this distance is 1. So the furthest away, or the furthest point of all of the petals is a distance of 1, and it's not an accident. It's because it's coming from the sine function over here. A couple of groups were sort of conjecturing, wait, I see 4 petals here, and I see sort of 4 humps there. So they were seeing maybe a connection, but it was fuzzy in their minds, because here some of the values are positive and some of the values are negative, and kind of how does that correspond to the 4 petals over here? So a great thing to do is to try and add more features to try and see which features match up. So I've written that here as think about the process behind the algebra. And we'd said that the process for plotting polar was to imagine plotting individual points as your angle gets bigger. We had sort of a data table where you start with a small angle and you make it larger, and you use the equation to figure out what the radius is. But this is telling us those values. So instead, let's make more connections. So from here to here, this is pi over 2. So this is like the first quadrant. This is 0 degrees to 90 degrees. And so as my angle goes from 0 to 90, the distance goes from 0 to 1 and back to 0. And so that's why we see, I'm going to draw a bunch of lines here, that's why we see as the angle goes from 0 to 90, you see that the points along that line go from a distance of 0 at the origin all the way out to here, where the distance is 1 when we're facing at 45 degrees. And then as the angle increases, the distance along the line goes all the way back down to 0 again. And so that way of thinking can start helping us piece together what's happening. Because just looking at this equation, you might expect this is the way you draw it. You might think you go boink, 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 boink. But if you really pay close attention to the connections, between 90 degrees and 180 degrees, all the distances are negative. So what that means is when our angle is facing in this quadrant 2, the distances are negative, which means you're actually plotting the points in the reverse direction. So if you're increasing the angle, you don't draw this petal first and this petal second. You draw this petal first and then this petal second, and this petal third and this petal fourth. And you can get all of this yourself just by thinking very carefully about the meaning of the algebra and then making connections. And the more features you can identify and the more detailed you can be, the more likely you'll see a connection that's helpful. Another example is the one that I showed you in class yesterday, but I thought maybe it would be nice to do a video of it. It was the test question where you're trying to describe the position of the dot in the Google app timer, the Google Timer app, where you type in a certain number of seconds and then the dot slowly moves in a circle as your timer counts down. So this is a great problem. Well, all right, so step back. If you want to practice the skills, go ahead and think about what are the basic things you know how to do in the unit, and then what are your problem-solving techniques, and think about what do you think might be appropriate here. So you can pause the video, give it a try. So for me, my top picks were writing what you know and what you want to know using math notation, solving the problem one piece at a time, because it turns out there's a lot of pieces to this, and then using other representations to be really clear in your own mind about what you know and what you want. So I know I want a circular motion. So if I'm just kind of, brainstorming, if I'm sketching, I know one of my basic ideas is if I've got cosine t sine t, I know that produces a circular motion because it's a length 1 vector centered at the origin that's just rotating once every 2 pi seconds, if t is in seconds. Okay, so the question is, how can I take this basic circular shape and make it fit this problem? And so I'm going to notice a couple differences. Well, one difference is this traces out a circular motion where the path is radius 1, because this vector is length 1. But here the vector isn't length 1. It's the radius of this circle is larger. So I know I'll need to scale it on the outside so it's the right size. And another thing I know I need to change is I need to change how fast it's doing the rotation, because here I need it to take s seconds to go up 2 pi radians, whereas here, whatever time it is being interpreted as the angle. So if time is 2 pi, that means that it has gone a full circle already. So the other thing I'll need to change is the angle. Is there anything else? Oh yeah, where it's centered. So this is tracing out a circular shape at the origin, but I know that I need to move it up here. And so so each of these is a basic skill we've done. We know about how vector addition, you can think about it as putting the vectors head to tail. And then that makes it really easy to translate a vector that's moving to a new location. So let's start sketching out these various ideas. I think I want a vector that's taking me to the middle here, and then another vector that's rotating. So I'll have two vectors. I'll have this A, and I'll have this rotating vector B. So my A vector is going to take me to the center, and then I'll have a B vector, which is going to be cosine something, sine something. And then I also know that I need to scale it to be the right size. So this is giving you a template. All I've done is I've written down what I want to know by thinking carefully about all the pieces. And so now I can start tackling these pieces one step at a time. Like, how do I actually move it to the middle here? And then what size should it be? And then how do I think about the speed? So the information that's given doesn't quite tell us everything we need, but hopefully it's easily calculated. So halfway between 90 and 320 was, I believe it was 205. And then this radius is 115. And again, you can do that sort of basic arithmetic. So if I'm going to go to the middle here, that's an x displacement of 205 and a y displacement of 400. So I've found that part. And then I know that my radius here is 115, so I'll scale my vector by 115. And then the last part I want to really focus in on, it might be hard for you to think about how to jump directly to an equation here that fits the situation. So this is where I like to use other representations. I think very graphically, so I like to draw little graphs. You could use a table, either way. But it's like, I know I'm going to have some expression with t inside here, but when I plug in a particular time, I need my math expression to give me the angle I want. So we're really describing a function, where the function's going to take time as input, give angle as output. So you could think about representing your function this way, time, angle. Or I like to do it graphically. So this is time, and the output is angle. So what do we know? What do we know about the problem? Or I guess you could think about it as what do we want to have happen? So I said that at time 0, we need the dot to start out up here. So that's an angle of pi over 2 radians. So in a table, I could say time 0 must be pi over 2 radians. Or in a graph, I could say time 0 must be pi over 2 radians. So I know, and again, what we're doing is we're trying to think about what function should we put inside here. But we're representing the function not algebraically, we're representing it using these other tools, so that'll help us think about what the algebra should be. All right, so what else needs to happen? I know that it needs to go 2 pi radians. It needs to go all the way around in s seconds. So you could think about it this way. In s seconds, I need to go pi over 2, plus another 2 pi radians. So this would be 5 pi, nope, that's wrong. it would be 5 pi over 2 radians if you were going to combine those together. And then same thing over here. After s seconds, I know I'm over here at pi over 2 plus 2 pi. All right, so I've represented it. Now all I have to do is ask, what's the equation of this line? What's the equation of this function? And you know how to find the equations of lines. So it's got a y-intercept of pi over 2. The slope is rise over run. So the rise here is from pi over 2 to pi over 2 plus 2 pi. So it's gone up by a total of 2 pi radians. It's gone over by s seconds. So rise over run is going to give us 2 pi over s. And that's the slope. So that's the coefficient for my independent variable t. So this is the equation that describes the relationship I want. And so that's exactly the equation I'd want to plug in here, because this equation lets me plug in a time, and it will tell me the angle that my point should be at. So you can see that there's a lot of steps here, but each step is connected to the other things in the problem. And that's what I want you to be focused on, is how can you use the basic skills you have and tools like graphs and tables to think your way through the problem step by step.